Hello everyone. In this video I'm going to address the elephant in the room. In the past video I spoke a lot about PCB design, electronics and algorithms. So one might easily think that building a multi-effects pedal is mostly about electronics, soldering and drilling holes into a Hammond box. Much like building small stump boxes, but just more of it. However, this is not the case. The glue that ties a DSP, which stands for Digital Signal Processing, multi-effects stump box together is software. 10,000 or even more lines of code define how the sound is processed and what the buttons do, and what is displayed on the tiny screen. Today I decided to talk about this subject. Okay, before digging into software, I just want to quickly demonstrate what the PiPicoFX is and what it does just in a few sentences. It's a multi-effects device with 3 foot switches, here and here and here, and 3 knobs up there, and a little display for showing various things, gain stages. It's mainly designed for microphones. You can either connect a high-set microphone using this upper entry or a standard dynamic microphone for the lower entry. You can choose various effects using the rotary encoder. Just switch delay, and in this mode the parameters can be changed directly, like having a stump box. And well, we can go further, can do various things such as running everything through an amplifier with loads of distortion and maybe also some echo added. It also has a second mode. This preset mode, so you can store different types of presets and switching between them. Like this is a reverb. You can also, the presets are organized in banks, so you can, by pressing 2 foot switches, as usual on this 3 knob device, we can switch banks. We have a little preview here. For example, if you want to change to large hole, we can press here. We have another reverb. Presets, let's maybe switch back to this one. It's a little bit better to hear. Presets can also be edited using these knobs. Then changing the mode. You can select the program for a preset. We can also then change the color of the LED. It's badly visible on the camera, but it could be changed. And then you can edit the parameters which make up a certain preset of a given effect program. I'm not going to show this into detail. Obviously we can change the name as well, and when we go back we can either save it or just leave it as it was. Yes. Yes, of course we can also change a little bit some minor system settings, like we can disable one input or output or change the overall volume level by always using the encoder and these switches to either select a parameter or to change it. That's basically it. There's another version of the PiPicoFX which also has a looper included. But well, I think let's go back into the internals, not even the hardware, but the software. Contrary to electronics, this is a bit closer to my daily business, but I'm not an expert nonetheless. Also, I find it really difficult to talk about code or to explain it. I try my best. This video is intended as an overview about everything software. Maybe I'll dig into specific parts in greater detail in later episodes. Today I'm touching the following subjects: programming languages, the IDE, which stands for Integrated Development Environment, building software, debugging, structuring an increasingly large software project, also known as architecture. Then we talk about tools, and finally round up by discussing the topic of asset generation. Around 20 years ago, I taught myself AVR assembly for some smaller digital electronics projects based on the trusty Atmega 8. Since then, I did small software projects both as a hobbyist and sometimes as part of my day job as well. There I used a wide variety of higher level languages such as C#, Java, PHP, Python, JavaScript, Kotlin, Fortran, etc. So when starting this project, I decided to go with C for the large part and only do some very specific parts in assembly. Also today we have AI support, which works badly or not at all for assembly. For scripts and various smaller tools, I decided to go with Python, since it's very easy to include additional libraries. The Make ecosystem has proven to be increasingly important. Therefore, as the project grew, I had to refine my Makefile quite a few times to have a stable and fast build system. That's why I list it also under programming languages. When working with Raspberry Pi Pico, one is naturally guided towards Visual Studio codes. Therefore, I stuck with it, although for STM32s the free STM32 IDE would be a more obvious choice. I actually also installed STM32 IDE and created a configuration project for the Daisy Seed board, which has proven to be handy for looking up clock speeds at different buses and obviously configuration settings. The downside was that I had a poor compiler setting to Visual Studio Code and stripping off a lot of unused compiler defines, etc. Other than that, there's not much to say about the IDE. I created a bunch of tasks for building and debugging, installed the Cortex debug and various other extensions, and that was it. Building. As an avid Linux user, I stumble over /configure, make install every once in a while. When I want to install the absolutely latest version of some FOSS application, usually for things like Android apps or larger desktop applications, I don't care about the build system too much. I just use the standard MyDSP Gradle, Maven or CMake. Embedded applications usually start off with a simple build shell script packing the most important commands together so I don't have to remember them. The PiPicoFX also started off like this. After a while it got too complex, so I dug into the working of Make to be able to build a Makefile capable of handling various targets for the PiPicoFX. After learning the basic of Make, I got aware that CMake also exists, which would further simplify build and make the build process platform independent. I was thinking about using CMake as well, but then shied away from the idea of investing a considerable amount into something which is not really of use, at least for me. Debugging. Back in the days when I experimented with Atmegas, I had two options at hand when it comes to debugging, including LEDs, UART and character display output. The second option was the Atmel simulator, which allowed me to debug on a virtual device. This of course also had its limitations regarding external input, for example. Luckily, for the Raspberry Pi Pico and for STM32s there are hardware debugger options available. For the Raspberry Pi Pico one can burn PicoProbe firmware onto a RP Pico to turn it into a USB SWI debugger. For STM32 the popular and widely supported ST-Link adapters exist. Unfortunately, we cannot use STM32 debuggers for non-STM ICs, so I went with ST-Link version 3 for the Daisy Seed and the Raspberry Pi Pico debug probe built into a little handmade wooden box for the RP Pico. For the Raspberry Pi Pico I invented my own SWI UART pinout. Unfortunately the powered parts are male, which is a huge design mistake, just to be clear, but it didn't bother me so far. Let's start with a quick overview of the system. At the core there is either a Raspberry Pi Pico board or a Daisy Seed board. In this video I'll talk mainly about the Raspberry Pi Pico version, otherwise it would get too widespread. Maybe this will be a topic for another video. The core board is attached to a custom PCB. It contains a few analog parts such as audio preamps, output stages and headphone amplifiers. As mentioned previously, this video is about software, so the digital domain is the center of attention now. It contains an audio codec which is configured by software over I2C. Data exchange is done using the I2S, which stands for Inter-Sound Interface. Since the Raspberry Pi Pico interface doesn't have a dedicated I2S interface, a PIO structure is used for this. Continuing with the internals, There is an EEPROM for preset storage attached to the I2C bus. The Raspberry Pi Pico board contains the RP2040 chips and some external flash storage interfaced over QSPI. Besides there is an external clock allowing a CPU clock of 200 MHz, making use of the PLL phase-locked loop. The user interface part or UI part consists of two parts. A root part depicted on the right side. It contains a 128 by 64 pixel monochrome display, a rotary encoder, 2 switches and 3 potentiometers. These controls exist since the first hardware rendition. The display is interfaced using SPI, the encoder and buttons are connected to the GPIOs and the potentiometers are read with the internal ADC. The second UI part consists of 3 stumpbox switches and 3 big bicolor LEDs. They are attached to an Atmega 88 acting as a port expander which communicates over I2C with the core. Let's drill down to the core of the firmware. Between powering up and powering down, the firmware passes 2 phases. A setup phase occurring only once, followed by an endless loop. Those who have some experience with Arduinos might recognize these parts. They are even present in this simple blink sketch for Arduino. Of course, our setup routine is a bit more evolved. There are things happening before and after the C part of the firmware, or the part written in C. First, the location of the interrupt vector is defined, then the stack pointer is set up. This is something I remember having done also for assembly programs for the Atmegas in my early days. Then we need to copy sections from flash into RAM in order to have memory content consistent with the layout defined in the linking process when building the firmware. If we wouldn't do this, variables would have the wrong initial value and function residing in RAM wouldn't be present, leading to an early crash. After this, various hardware parts are initialized in a sequential manner. First, the CPU clock is brought to the correct speed, allowing the initialization to happening afterwards to be done at full speed, 200 MHz. Instead of the initial 6 MHz, the Raspberry Pi Pico is clocked by default after powering up. The phase-lock loop for USB setup, followed by the system tick timer. This is a timer unit built into the processor, allowing time measurements in a 10 milliseconds resolution for this specific firmware. This time is mostly used for UI-specific wait routines happening in the subsecond 2-second range. The DMA, we'll talk about this soon, is initialized, followed by various hardware components such as GPIOs, the PIO to emulate the I2S interface, another timer, the ADCs, the I2C hardware, the audio codec. As seen here, I already iterated over quite a few different ones. The first version used the WM8731, then came the CS4270, now I'm working with a PCM3060. Later on, some software components are initialized and the second core is started. If some preprocessor flags are set, USB and UART are initialized as well. This I use for some specific debug situations. At the end of the setup routine, the I2S driver is started. By that time the codec is already running. Since the RP2040 is a dual-core processor, it is beneficial to use both of them. At least for this case where processing speed is critical and power consumption isn't. So there are 2 loops, one for core 0 and one for core 1. Looking at the loop for core 0, it seems to do almost nothing. If a variable buffer count is larger or equal to some constant, constants are generally uppercase, following a widely used C naming standard, it is reset to 0, then a bit in a variable called task is set. We don't know, just by looking at one loop, how buffer count ever could change. We don't get an answer either by looking at core 1 as well. Core 1 seems to do a little bit more. If some bits in the task variable is set, some fractions of code are executed. Depending on the bit set, different methods are called, effectively propagating hardware change to the application layer. If the knobs have changed, for example, on knob is called, if update audio UI is set, on update is called, etc. Update audio UI would be set within core 0, within the core 0 loop, but we still don't know how this might ever happen. The answer to this is interrupt. An interrupt is a jump of the program count to a specific address due to an event. The method jumped to are generally short. They handle time-critical stuff such as reading out hardware buffers, then placing the result in a potentially larger buffer. Before explaining the different reasons why the program execution within the PiPicoFX is interrupted, let's quickly state one important principle. The most important task of an audio effect device is to process audio, obviously. Everything else, lighting LEDs, reacting to button presses, displaying something on the display, is way less important than seamlessly reading samples, processing them, and placing the result in the DAC, digital to analog converter buffer of the codec. One interrupt is occurring when the codec received or sent a certain amount, 16 in our case, samples. So, further, when time has elapsed, one line is written to the display, data from the add mega is received, the state of the enter and exit switch has changed, the rotary encoder is increased, and some inter-core transmission happened. Also, interrupts are generated. The latter is due to the fact that sometimes both cores are used to do some heavy computation when processing samples. Let's finally solve the riddle why the core 0 loops make sense. The interrupt triggered when the codec received or sent samples is handled by core 0. All other interrupts are handled by core 1, except the SysTick counter, which exists for both cores simultaneously. Within the interrupt routine handled by core 0, buffer count is increased. This finally is the missing link, explaining the reason of the existence of the loop of core 0. Opposed to the principle mentioned earlier, the interrupt routine of core 0 isn't line to wait or returning quickly. But remember the principle mentioned earlier, the most important task of an audio effect device is to process samples. Therefore, when this happens, the processing needs to be done right away with no further delay. When not doing so, there are more or less frequent clicks. These occur when audio processing has been finished too late, overwriting the array currently being processed. Of course, this could be mitigated by increasing the buffer size, but this again would increase latency. In an interrupt routine, in general, hardware is reconfigured, some flags are cleared, which prevent the CPU to re-enter the interrupt routine right after exiting it, and information is persisted. In most of my ARM Codex projects, also a bit of a so-called task array is set, indicating non-time critical work to be done. This is an example of an interrupt routine of the PiPicoFX firmware. The interrupt routine is entered each time something happens on the I2C bus. By the way, if you don't know what I2C is, here's an excellent tutorial on this subject. There are three cases. Case A is when a hardware receiver buffer is full, then the content is copied into the array data of a data structure I2C received data. By the way, we just assume that the data array never overflows, which is slightly sloppy coding, I think. Anyways. A second case B occurs if a start condition is detected. Then the number of received bytes is reset to 0, only if there's no task I2C data received is pending in the main loop. The third case is when a stop condition is detected. If there is no task I2C data received pending, the number of bytes received is stored in the I2C received data, and the aforementioned task is set pending. There is also a fourth case when a transmission has been aborted. This can occur because we have a multi-master I2C setup. This again might be topic for another video. Let's talk about the task array. This is kind of a poor or dumb man's multitasking. Generally, within interrupt routines, a data bit is set indicating non-time critical tasks can be done in the main loop. Each bit stands for one task. Of 32 possible entries, only around 5 are used. The task array has been taken from other projects of mine, that's why some unused entries such as task of reception or transmission of UART data over Bluetooth exist. The mechanics of task is similar to interrupt, with the difference that the order of the processing is never changed. Also, one task can never interrupt another. That is why it's called poor man's multitasking. In a real multitasking OS, this could happen anyways. There is one component we have to talk about to conclude the driver part of the firmware. This is Direct Memory Access, or DMA in short. The DMA essentially is a hardware piece capable of copying data from location A to B without using the CPU. It essentially offloads a piece of code such as this from the CPU. Most DMA implementations allow to define the repetition or the data amount to be transferred. They also allow to define the pointer increment. Generally, when copying data from memory to memory, both pointers are incremented. When copying from hardware to memory, only one pointer is incremented. Also, some kind of flow control is supported, prohibiting premature read of hardware buffers, for instance. Also, most DMAs can interrupt the CPU when a transfer finishes. In the PiPicoFX, DMA is used for multiple purposes: to fill the audio buffer from the codec, to feed the codec from the audio buffer, feed the SPI from the display frame buffer, and to update potentiometer values from the ADC readout. We're slowly but steadily reaching the application and user interface layer. Regarding the most important task, audio processing, there is one detail we need to address. In order to have a strictly sequential audio stream, we employ a double buffering scheme. This means that when one of the buffer is transferred to or from the codec, the other one can be processed by the interrupt routine. This doubles the memory requirements but prevents discontinuities in the audio buffers. For the display, only a single buffer is used, resulting in rare glitches, which is acceptable. Since the PiPicoFX is a multi-effect device, another crucial task which needs to be handled really well is a seamless switching from one effect to another. For this to happen without clicks or artifacts, a careful communication of the main loop with the audio driver is necessary. After the UI has detected a condition requiring a program change, the main loop requests a program change by modifying a program change state variable. This happens only if there is no previous program change pending. In the audio loop, then a fade out happens within 16 samples. This is 0.32 milliseconds. After this, the main loop is notified that the new program can be loaded. While this is happening, the audio driver simply bypasses the processing function, resulting in the input being forwarded right away to the output without modification. After this is done, the program change is modified once more, indicating the audio driver a fade in for the new program can be done, again over the course of 16 samples. Then the program change state is reset. The PiPicoFX firmware revolves about two fundamental types of objects: the UI pages and the effects processor. By the way, the two is also an excellent acoustic Metis blues duo that I had the chance to witness a few times already. Sometimes they play as a duo, sometimes in larger setting, including drums, bass, percussions. In essence, the two are two voices and two guitars. Well, anyways, switch back to our dry software topic, shall we? UI pages define what is displayed on the screen, but also define what happens when the UI elements are manipulated. For example, in the live mode, the potentiometer changes some parameters of the effect program, and the stomp switches causes a change to another page called the preset page. There the stomp switches change the presets and the potentiometers don't do anything audible. The UI pages are coded in C. Each UI page is a set of methods manipulating a global UI data structure. The effect programs on the other side are proper C++ classes. More on why some parts are in C++ later on. The effect programs contain parameters, which are changeable setting of the program, and the crucial method which takes samples and processes them. Let's shed some light onto how an event from the main loop is propagated to the currently active UI page. We have already seen that the main loop calls on something functions when bits in the task array are set. These in turn are set in the interrupt routines. The interrupt routines are fired on physical hardware events. These on something functions are part of the UI controller. What this does is simply propagate the function to a callback if it is registered. Besides, the UI controller allows to register and unregister callbacks, effectively changing the behavior of the user interface. Each UI page can contain the following callbacks: enter, which is called when reloading the page. This should fill the frame buffer with static content in its variables, etc. Update, this is called in regular intervals in a 10 Hz frequency. There we should update the frame buffer with dynamic contents such as the levels. Then we have knob callbacks. They are called when the value of the knobs changed. Button callbacks, these can be registered with pressed or release events. And enter function, this is called when the page is entered. This in generally unregisters previous callbacks, registers new ones, and then calls the enter function. These code snippets show the template of a UI page. This template is included in the code base, allowing to easily add new pages. The functions are empty by default, except for the update function, which should notify the display driver to update the display from the frame buffer. Otherwise, there will be no dynamic content on the display. The UI controller mostly does what I explained before: call a function given a function pointer is not null or not zero. By the way, null and zero is used synonymously in this code. For me, as a hardware guy, it's basically the same, although it's probably bad coding practices. One functionality the UI controller provides, besides effectively handling null pointer exceptions, is to provide a mechanism to automatically going back to the page visited previously when pressing exit. This relies on the following. Each page is numbered starting from 0. All the enter functions are stored in an array whose index is the program number. For example, UI enter function 3 bracket data calls the enter function of page 3. Page 0 is the first page, by the way. When jumping off, the page number can be stored on a UI stack. When the exit button is pressed, the onExit function of the current page is called if present. Then the enter function of the page, which is on top of the UI stack, is called if it's not 0xFF. At the same time, the page number is removed from the UI page stack. This auto-return removes the need for each page to store the value of the previous page, since in many cases we want to go back somehow. However, the mechanism is often locked by pushing 0xFF on the stack, so I'm not really sure how clever this really was. We're nearly done describing the overview of the PiPicoFX software. There's one last thing I'd like to mention. At the same time, I want to give insight in which direction the PiPicoFX, soon to be called either Open Stomp Effect or Free Stomp Effect, evolves. When developing the firmware, I gradually added effect program by effect program, enjoying every new possibility it had. Except for the delay memory buffer. This is a very long buffer which is needed for delay and delay-based effects. Every program has its variables statically loaded. This layout was initially very simple. Also, I had a good control of the memory usage. Also, switching from one program to another required little computational effort and is always possible. The cons is that every effects program can exist only once. At the beginning, I thought the processing power probably doesn't allow more than one program to be running at once, either in parallel or in series. However, especially after some important performance improvements, this is not true anymore. One next step that the device is going to take is to allow a user-definable combination of effects to be present. This requires dynamic loading of effects program. For this, there are two options available. One could of course use malloc and free to dynamically allocate memory. However, handling effect programs and parameter changes would still be clumsy and unintuitive. So I decided to swallow the bitter pill and to migrate some part of the firmware to C++ and handling the effect programs as proper objects. This much simplifies handling effect programs, enabling the addition of complexity in the combination of effects and parameter manipulation. However, it also complicated the build process. Furthermore, I was worried that the performance could be impacted negatively. Luckily, this was not the case, in contrary, especially for the Daisy Seed version. Besides the real firmware, also a few smaller software tools have been created for various tasks. For the development of digital filters, I put together a Python script which visualized the maths I didn't really understand, and still don't understand so far. Also, it helped me to predict if a filter is stable, processing a sample as expected, or unstable, resulting in deafening noise given certain input signals. Another tool which has become increasingly important is the offline processor. This allows me to process WAV files through the exact same sound processor functions as the real hardware, without the need to flash the actual firmware. For this, parts of the C++ code is compiled on an x86 platform, resulting in an executable which takes input and output files and the effects program and parameters as command line arguments. To have a graphical user interface as well, a Python frontend has been done using tkinter. Lastly, several tools for the processing of assets within the build process have been developed. Opposed to character displays with dot displays, one has to think about fonts sooner or later. On the web there are a few open source font maps available as C-header files. Usually I go with a standard 5 by 7 pixel character font which fits nicely into the vertically aligned bytes of the OLED displays. For this project I use the GFX fonts from Adafruit, which allow a greater variety of sizes and styles. Besides fonts and primitive shapes, the PiPicoFX also contains images. These as well have to be transformed from the visualization into bits and back. For very small images one could go with the hard way and write the C-header directly. I decided to invest a little bit of time into a tool which converts a black and something PNG file into a C-header using Python with the appropriate image processing libraries. This concludes the video. Thanks for watching and see you in the next episode. Goodbye.